Hello, today we're going to cover the next topic in our plan. Specifically, we're going to talk about Hessians. And so we consider we consider the multivariate function. So it's a function that takes the points in n-dimensional Euclidean space, and it outputs the value, the scalar. And we previously discussed the gradient, the notion of the gradient, and we said that each component of the gradient, it's a partial derivative of the function. But now we know that this partial derivative itself is a multivariate function. So it takes also the inputs in n-dimensional Euclidean space and outputs the scalars. Therefore, we can ask the question, but what if we will take the gradient of that partial derivative itself? Following the definition of the gradient, we know that the gradient of the function, of the partial derivative function, consists of the partial derivatives with respect to each component of that partial derivative function. So notation-wise, it will be presented by this vector. It's also a dimensional vector, where you see that each component of the jth partial derivative, we first take the partial derivative with respect to x1, the first component, then partial derivative with respect to x2, x3, and so on. And when we combine all these gradients of all the partial derivatives column-wise, so you see that the first column in that matrix is the gradient of the first partial derivative. The second column in that matrix is the gradient of the second partial derivative of the function f. The third is the third, and so on. As a result, we got the n by n matrix, where n is the dimensionality of the input. And that matrix is called Hessian, or the matrix of the second derivatives of the multivariate function f. Let us consider this quick example, how we compute the gradient of already familiar function that we discussed previously in our gradient slides, at exactly the same point, x0, which is 1, 3, and 5. So remember that following the definition, the first column of Hessian will be the gradient of the first derivative, of first partial derivative, df over dx1. And from the previous lecture, we know that for this specific function, this partial derivative, first partial derivative, is equal to 2x1 plus x2. So now we take a gradient of this 2x1 plus x2. Again, following the definition of the gradient, we take a partial derivative with respect to each component. And first, we take partial derivative of 2x1 plus x2 with respect to x1, then 2x1 plus x2 with respect to x2, and then 2x1 plus x2 with respect to x3. And as you see, because this is a linear function, it just gives you this vector 2, 1, 0. And that's a vector which is constant, and it turns out that for this specific example, it doesn't depend on the point x at which it's evaluated at all. But of course, when we go for the second column of the Hessian, we need to take a gradient with respect to second derivative of the function f. And we remember from our previous slides that the second partial derivative of function f is given by this expression, x1 minus x3 cubed divided by x2 squared. And for this, we already see that we will not see the same situation as for the first partial derivative, where it was actually a constant vector. So again, following the definition of the gradient, we take the first component will be the partial derivative of x1 minus x3 cubed divided by x2 squared with respect to x1, and it's 1. Then for the second component, we take the partial derivative with respect to x2, and this already will be some expression, 2x3 cubed divided by x2 to the power 3. And finally, when we take the third component, which will be the partial derivative with respect to component x3 of the expression x1 minus x3 cubed divided by x2 squared, it will give you the result minus 3x3 squared divided by x2 squared. And finally, for the third column of the Hessian, we take the gradient of the third partial derivative, and this partial derivative is represented by the expression 3x3 squared divided by x2. And again, following that definition of the gradient, we take the partial derivative of this expression with respect to each component. And as a result, we get this vector 0 minus 3x3 squared divided by x2 squared and minus 6x3 divided by x2. So as a result, we combine all these three vectors column-wise. 2, 1, 0 was the first column, which was the gradient with respect to first partial derivative. Then the second column is the gradient with respect to second partial derivative. And finally, the third column is the gradient with respect to the third partial derivative. And we got the matrix, which is 3 by 3 matrix, which is correct because our in this example, our multivariate function is operating on three-dimensional Euclidean space. The general expression at any point of the Hessian of this matrix is presented here. And because now we want to evaluate this at this specific point 1, 3, 5, we just need to substitute the corresponding values of these components in this expression here. And as a result, we arrive to this matrix. And that's as Hessian of this function f, evaluated at point 1, 3, and 5. Now, previously, we also discussed the geometric interpretation of the first of the gradient. If you remember, we constructed the tangent lines. So let us quickly recall that. So assume that we have some function in n-dimensional Euclidean space. So here, the n-dimensional Euclidean space basically illustrated by these two axes, this one and this one, and the value of the function is the corresponding value here. So then the tangent line to the function f of x at the point x0 has this, by the definition, is this surface, is this plane, where x is the point that changed the values, and everything else are constant. And of course the gradients, it's a gradient of the function evaluated at the point x0. So the only thing that varies in that expression is this x, and everything else is basically defined by the function at the point itself. And we already know that the meaning of that tangent line is that locally around the point x0, this tangent line gives us the good linear approximation of the function. So in that shaded purple area, the values of the function will be very, very close to these points on that surface, on that plane, on the tangent plane. That's why we said that it's a linear approximation or first order approximation of the function locally. But please keep in mind that's only local property, because of course this plane cannot be considered as a good approximation for the function anywhere from the point x0, like far from the point x0, as you see for this specific example. But locally in this very, very small neighborhood, typically it's also depends on how our function acts. But locally there's a small neighborhood around the point x0 where this tangent line gives the very, very good approximation for the function, for our multivariate function. Following the same idea, now we can define the tangent second order surface, and this is exactly where our Hessian will play a crucial role. So the tangent second order surface is defined by this quadratic expression. Why this expression is quadratic? Because the variable x here is basically participate with the degree of 2 expression, which is this quadratic expression here. So x, you see this is basically product of the vector x minus x0 transpose multiply on the Hessian and multiply on the x minus x0 again. So, and that gives you the scalar. The whole this expression is just will be a scalar expression, the scalar value. And similar as for the tangent plane, everything is defined at the point x0 using the gradient, the function value itself, which also called the zero order approximation. Then this is a linear term, which is defined by the gradient of the function f evaluated at the point x0. And also now additional term, this is quadratic term, which is defined through the Hessian of the function f evaluated at the point x0. And similarly, as we have for the tangent plane, tangent second order surface also allows us to approximate function x0 around some neighborhood of that function with a good accuracy by basically approximating that with this quadratic with this tangent second order surface, and that is called quadratic approximation of the function. So in order to of course we can actually generalize that. We can consider the each entry of the Hessian. We can consider that entry as a multivariate function itself, and therefore we can actually continue differentiating that, constructing so-called higher order derivatives of the multivariate function, and typically they are presented through tensors. If the function is good, and the good is as we agreed to call, it's a smooth function. It's a function that has infinitely many derivatives, and all these derivatives are continuous functions. Then we can actually, there's a theorem in mathematics that tells in calculus that tells that this function can be approximated at point x with this in the neighborhood of the point x0, in the neighborhood, in some neighborhood of the point x0. It can be related with this so-called Taylor series. And the Taylor series, we have value of the function x0 plus the linear term plus the quadratic term and so on. And here x should take the values which are not that far from the point x0. So that's why it's called neighborhood. All of that, it has this locality, local, only valid in some local neighborhood around the point x0. So as we said, this is the linear term, this is a quadratic term, and this is higher ordered approximation, which is defined through the, as I said, through the tensors for the multivariate function. Now, let us see the concrete example how it works, for you to grasp the idea of this approximation, and the quality of the approximation. So let us consider the very simple function sine of x. And let us assume that the point where we want to approximate that function is the point 1.8, just this simple point. Then g0 of x, which is just the value of that function at this point, it's called zero-order approximation. So the zero-order approximation in this plot is this green line, and the blue line represents this function sine of x itself. So this point here, 1.8 somewhere here, it basically will give us the value of function, and the zero-order approximation is just equal everywhere. It's equal to the value of the function sine of x at the point 1.8. And as you can see, it's a very crude approximation because it only coincides with the function sine of x is just in that point 1.8, and not it's not equal to that function in the neighborhood of the point 1.8. That's why we usually say that it's a zero-order approximation. It's quite inaccurate, quite crude, because the size of the neighborhood around x0 with this approximation really valid is basically here it's equal to 0. It's only in this specific point. Now we will consider the tangent line, tangent plane, or as we said, it's a linear approximation. The linear approximation following this formula for the tangent plane is given by this expression here. And please notice, I'm sorry for this slope annotation, this sine 1.8 comma, it's actually derivative of the function sine of x evaluated at the point 1.8. It's not the derivative of the constant. So we need to take a derivative of the sine of x, which is a cosine of x, and then we evaluate that cosine of x at the point 1.8. And this basically gives, as we know, the slope of this tangent line. So this tangent line here, it's this green line, and as you can see now, it's actually not just gives the exact value of the function of sine of x at the point at point 1.8, but also actually in some small neighborhood around this point 1.8, x is equal to 1.8. It actually gives the value which are quite close to the function. So therefore we say that, oh yeah, that's already better approximation than just a zero order. So we already can speak about some locality where this tangent line gives us values which are quite close to the values of the function. Now let's see the third order approximation, well, second order approximation, which is given by this tangent second order surface, and then following the expression of that, we can actually get the form, and it will be given by this parabola here. And this parabola, as you can see, it already gives very actually good approximation, already in quite big neighborhood around the point x is equal to 1.8 for the function sine of x. So this parabola here is a green line, and the sine of x is the blue line. And of course, if we consider the higher order, let's say this cubic function and so on, we actually get we increase the neighborhood where the quality of the approximation for the function sine of x will be better and better and so on. So that's the basically say illustration for the Taylor series and the geometrical interpretation of the Hessian and higher order and differential operators for the multivariate function. Now let us quickly discuss the extensions of the gradient. So we'll consider two such extensions. Previously, we discussed the case where our function was a multivariate function. So it actually, what does it mean? It takes points in empty n-dimensional Euclidean space and returns the scalars, so just numbers. But also we can consider mapping or multivariate vector functions. So what's the difference? The difference that they also take as input, they take a value points in n-dimensional Euclidean space, but they output not just a scalar, but a vector as well. So basically here we have such general form of that mapping F. So it takes n-dimensional Euclidean n-dimensional vectors in Euclidean space, and it output m-dimensional vector itself. So typically this function can be written as a vector where f1, f2, and fm are the corresponding components of that vector function or mapping. And now, yeah, each of these, please notice, each of these component is a multivariate function itself. So basically, because it takes the n-dimensional vector, outputs just a value, just a scalar. But when you combine them, you combine them in the vector. That what gives you the value, the output of the mapping. Now, you also can ask, but how we can define now the gradient of this mapping? Of how we define the derivative of the mapping? Well, by the definition, the derivative of the mapping is defined by taking is defined by this matrix, m by n matrix, where on each row we basically just take the gradient of the corresponding component of that mapping. So in this specific case, we have this vector function of f(x), which can be represented as a vector of multivariate function f1 of x, f2 of x, fm of x. Now, in order to define the gradient of that multivariate mapping, what we do, the first row of that gradient will be nothing but the gradient of the first component function, f1. The second row in that matrix will be nothing but the gradient of the second component of that mapping f. And finally, the last row in this matrix will be nothing but the gradient of the last component, fm of x, of this mapping function. So this is the gradient of the first. This is the gradient of the second component of f(x), and finally, it's the gradient of the last component. And in mathematics, that expression is called Jacobian. So Jacobian is nothing but basically the gradient of multivariate vector function. And its size, it's m by n, where m is number of rows, and it's equal to the number of components in that in the output of the vector function. And n is the dimensionality of the Euclidean space on which this multivariate function is operating. So where it takes the inputs and process the inputs. So let us consider the quick example of that. Consider this mapping. So it's a two-dimensional mapping that takes three-dimensional inputs. And let us evaluate its Jacobian at this specific point 2, -1, and 0. So following the definition, like this Jacobian is a 2x3 matrix, where in the first row we have the gradient of the first component, which is x1 squared plus x2 multiplied x3. And in the second row, we have the gradient with respect to the second component, which is x3 minus x1 squared and x2. And basically taking these partial derivatives, you can easily see that this Jacobian, the general form of the Jacobian of this mapping is given by this 2x3 matrix. And in order to evaluate that at the point x0, we just need to substitute the corresponding values of the components in that expression. And this gives you this the corresponding Jacobian matrix here. And the second extension that we're going to consider here, and that will be useful, especially when we will consider the back propagation for neural networks, it's the matrix functions. So it's previously we considered the case where function took the input in just n-dimensional Euclidean space and outputs either the value, so that was multivariate function, or that was the vector, which was multivariate mapping. But now we consider the case where the function takes a value which is a matrix, n by n matrix itself, and outputs the scalar, just number. So that's called a matrix function, and it inputs x is n by n matrix, which is can be written in the general form as presented here. And now we also can ask a question: what is the gradient of the matrix function? So by the definition, the gradient of the matrix one, which is the gradient with respect to matrix x here, is basically given in general by this expression, and this expression itself is m by n matrix, and the corresponding component, the ij component of this matrix function, is nothing but the partial derivative of the function with respect to ij's component of the input matrix. So keep in mind that when we can see the gradient is a special case of a matrix function where your matrix has just one column. Like here, in other words, n is equal to 1. So and it have m components. Then this gradient matrix will be just nothing but just here the first row, which is m-dimensional vector, which is already know that it will be the partial derivative of the function with respect to all the components of the input, which will be a gradient. But this is like extension, generalization of the notion of the gradient to the case where the function eats matrices and outputs the values. And it will be just m by n matrix. Again, let's consider the example, the short illustration for that. So we have this matrix function f of x, which is nothing but the trace of x transpose x. The reason why we choose specifically this example, because typically this x transpose x structure, the product of the matrix transpose on itself, will be quite popular in machine learning, and it's quite actually useful to be able to operate with this function. And the trace operator, you already know the trace of the matrix is nothing but the sum of the diagonal entries of that matrix. So in order to compute the gradient of that matrix function with respect to matrix x, let us look more carefully at the function itself. So x transpose x can be written as this product, and you can see that x transpose here is just a transpose of this matrix. It's n by m, and x itself is m by n. And now, if you follow the rules how we multiply the matrices, you can see that the diagonal entries of this matrix will be given by this expression. Let's actually check that. So in order to compute the first diagonal entry, you need to take the first row of the matrix and multiply in the first column. And that's exactly the expression here. In order to compute the second diagonal entry of that matrix, you need to take a second row of the matrix X transpose and multiply on the second component on the second column of the matrix X, and it gives you the expression, the second diagonal entry here, and so on. And finally, in order to compute the last diagonal entry of the product of this matrix, you need to take the last row of the first matrix, which is X transpose, and multiply on the last column of the matrix X here, and it will give you this expression. The reason why we focus on these terms, because as we agreed, we need to, in order to compute function f, we need to take a trace of that product. And for the trace, we don't need to know all other entries. We just can focus only on the diagonal entries, which we computed here. Therefore, following the definition of the trace is nothing but the sum of all diagonal entries. And you can check that this sum of all diagonal entries in this specific case will be given by this quadratic double sum expression, sum of all the squares of the entries of the input matrix X. And for those who actually remember our lecture on the Frobenius norm, that be basically nothing but the square of the Frobenius norm of matrix X, which is trace of X transpose X, and we just actually get this expression again. And now, in order to compute the derivative of that function of X with respect to matrix X, following this definition, we construct this matrix here, and this is M by N matrix, where each component will just take the corresponding we take the derivative of this sum of the squares of the entries with respect to corresponding component of the input matrix. And if you take these derivatives, you will see that all these partial derivatives, component-wise, when you take them, it will give you that matrix. And you'll see that 2, 2, 2, 2, 2 are common multiplicative term, so you can put it outside of the matrix, and then as a result, we'll just have 2 multiplying the matrix X. What we just proved is that the matrix gradient of trace of X transpose X is nothing but 2 multiplying X, where X is the input matrix, and therefore, if we want to evaluate this at the input X0, which is that matrix, it will be nothing but 2 multiplying that matrix, which is this matrix here. And it's important that also the very good exercise for you guys to try is to consider this expression, this function A transpose X B, where A, B some fixed vectors, and m-dimensional, n-dimensional respectively, and X is M by N matrix. And to show that if we take the gradient, the matrix gradient of this A transpose X B expression will give us A B transpose matrix. Just it will be a very good exercise to start to basically quickly understand these component-wise derivations and component-wise differentiations, and also it will give you basically a quick ability to properly understand how the dimensionality of these operations will be calculated. So then it will be basically it will be a very important skill if when we later will consider the back probe, and you will basically need to understand how different dimensionalities interplay between each other. Yeah, and of course, if you have any questions, you could write a comment, and we'll be glad to answer. And thank you very much. I think that's the end for today. Please like and subscribe. Please feel free to ask any questions. It's a for us, it's very important to have a feedback from you guys. And next, we're going to talk about backprop. And thank you very much.